right, let's take a look at what the FAA wants you to know about aircraft structural repairs. And not many of us are going to be repairing something like this. It looks more like a tin roof. Obviously, it's a Ford Trimotor, a beautiful thing. But the FAA does want you to know a few things about design of aircraft. For instance, they're going to ask you what a monocoque fuselage is. Well, a monocoque fuselage derives its principal strength from the actual covering of the metal or plywood. So the actual covering gives its principal strength. They also want you to know about a semi-monocoque fuselage. And the parts of a semi-monocoque fuselage which prevent tension and compression from bending the fuselage are the longerons and the stringers. And the longerons and the stringers are the longitudinal, that's fore and aft, structural members of the semi-monocoque fuselage. So here's your longerons and stringers. By the way, the longerons are the big pieces and the stringers are the smaller ones. They also want you to know about a cantilever wing. A cantilever wing is one that uses no external bracing, and this is a great example of a cantilever wing. It's a Piper Archer II, uses no external bracing. It has no struts on the outside of it. All right, now let's take a look at making layouts. Now, layouts is taking a piece of sheet metal and bending it to a shape. And the most important factors you need to make a flat pattern layout according to the FAA are the radius of the bend that you intend to make, the thickness, and the degree of a bend. So here's figure 4 in the FAA course book, and the FAA question book, I should say. And here's a piece of metal that we're going to bend to this shape. Now, when it's flat, they call it a flat pattern layout, and you mark off where you're going to make the bend. Well, you need to know such things as the radius of the bend you're going to make before you make this bend, the thickness of the bend, and how many degrees you're going to bend it, more or less than 90 degrees. Now, when you're bending a piece of aluminum alloy, and you're using a minimum radius for the type and thickness of the material, the layout should be made so that this bend will be 90 degrees to the grain of the sheet. So when you're bending aluminum alloy, the bend should be 90 degrees to the grain of the sheet. Now, when you're bending metal, the material on the outside of the curve stretches. So out here on the outside, the material on the outside of the curve stretches while the material on the inside of the curve compresses. So the outside stretches and the inside compresses. Now, the part of the material that when you're bending it that does not either stretch or compress is called the neutral line. So if you could find the spot here that didn't either bend or compress, that's called the neutral line. Now, sometimes you have to compute a bend allowance problem, and you could use bend allowance tables normally, but if bend allowance tables are not normal or not available, what you want to do is estimate this neutral line. Well, if you want to estimate the neutral line, the neutral axis of the bend can be found by adding approximately 1/2 the stock thickness. So the neutral axis, you can estimate that as 1/2. Now, let's take a look at the bend radius we're talking about up here. When a piece of sheet metal is bent to a certain radius, the curvature of the bend here is called the bend radius. So the curvature of the bend there is called the bend radius, and I want you to know that. Now, unless otherwise specified, the radius of a bend is the inside radius of the metal being formed. And by the way, the sharpest bend that can be placed in a piece of metal without critically weakening the part is called the minimum radius of bend. That's the sharpest bend you can make without critically weakening the part. Now, they're going to ask you some questions on the test about terminology involving metal bending. So let's you and I bend some metal, and we'll cover those questions about terminology. First of all, what we have here is a metal brake that's used to bend metal. It consists of a bed like so that you put the metal on. And then, of course, you have a shoe that comes down and clamps that metal down. And then you have a bending leaf that bends it up. There's a hinge right here in the bending leaf, so the bending leaf comes up and bends the metal to vertical, and now you and I have bent some metal. Now, let's cover some terminology you need to know about. The metal will have a flat area, and at one point it'll switch to a curve. When the metal goes from the flat to the curve, that point where that happens is called the bend tangent line. You can draw a line where you want that to happen, and that'll be the bend tangent line. That's the line from when the metal goes from flat to curved. You got that figured out? Now, let's assume that you want to know where to put the nose of the shoe. You do not put the nose of the shoe at the bend tangent line. What you do is you go up 1 radius from the bend tangent line. That's where it stops being flat and starts being curved metal. You go up 1 radius from that bend tangent line, and then you can draw another line. That's called the bend line or the sight line. That's the bend line or the sight line, and that's actually where you put the nose of the shoe. And the reason there's a difference is even though the metal starts curving here, it'll bend around this curve, and the inside of the metal then will be right at it, when it's vertical here, will be right at the nose of the shoe, and that's called the bend line or the sight line. Now, if you take the thickness of the metal, that's the distance between the inside of the metal and the outside of the metal, and that'll have you right out here where the metal becomes vertical, and that's called the mold line. So they're going to ask you, what is setback? And setback is the distance from the outside of the metal out here, the mold line, all the way back, including the thickness of the metal and the radius, all the way back to the bend tangent line. So the setback is equal to the thickness of the metal plus the radius. So one more time, let you and I go through these terms. The bend tangent line is where the metal quits being flat and starts curving. The bend line or sight line is where you put the nose of the shoe. The distance between those two is 1 radius. The mold line is the outer edge of the metal out here. You add in the thickness of the metal, and that gives you the mold line out here. And the setback is the distance of the thickness of the metal plus the radius. So let's take a look at exact wording, exactly the way they're going to ask you the questions on the test. They're going to say the bend line or the sight line on a sheet metal flat layout. That's what we have here. To be bent in a cornice or a box break, that's what this is, box break right here, is measured and marked 1 radius from the bend tangent line. Now they're saying the sight line is marked 1 radius from the bend tangent line. And they're going to ask you which bend tangent line are we talking about, and that's the line closest to the one to the end placed underneath the break. It's this line right here, 1 radius away, and you have the bend line or the sight line. If you can figure out the FA's language, you've got it made. Now, what is setback, they're going to ask you, and the setback, the amount of setback, is equal to the thickness of the metal plus 1 radius. Now, let's assume that you're going to bend some metal. Let's go to figure 4 and let you and I bend some more metal. Here we have figure 4. And we want to figure out how much metal to use to make this piece. Well, first of all, we want to know how far the flat is on each place, and then you add the bend allowance. Now, to figure out the flat, what you do is take the total distance and subtract the setback on each leg. Here's a leg vertical here, subtract the setback there, and here's a leg, the horizontal leg, subtract the setback there. Now, what you do is you take the total distance you want to go, subtract the setback, as we have done, and then add in what is known as the bend allowance. And up here it tells you how to figure out the bend allowance. And as you can see, it's a complicated formula. But what you need to know is to figure out how much metal you're going to use for a part like this. You figure the total distance of each leg, subtract the setback on each leg, and then add in the bend allowance. Let's do another question on figure 4. Let's assume we want to find the length of flat A, and that's the question they're going to ask you. Well, they give you this 4 inches right here, and you want to find the length of the flat A. Now, flat A is the area that does not bend at A here. Well, what you do is you take this total distance and you subtract the setback, and the setback is radius plus the thickness. Now, if you look at it, the radius here is 3/16 of an inch, and let's see if we can find out the thickness, and the thickness is over here, and it's 0.0625 of an inch. All right, now, what we do is we find out how much the setback is by adding those two together and subtract it from the entire distance of 4 inches. So let you and I take a look at the figures to do that. First of all, the radius plus the thickness is 3/16 plus that 0.0625. If you use your calculator and take 3 and divide by 16, you'll get 0.1875. Now add that to the thickness of 0.0625, and that gives you the setback. Now remember, this whole distance here was 4 inches, so you subtract the setback, and flat A is 3.750. So that's how you would figure out flat A. That's the part that does not bend in this drawing. All right, now let's take a look at the total layout dimension. That's the total sheet when it's laid out. And how do you find that? Well, you total the individual flats and the bend allowances. And here's figure 7 out of the FA book. And you have this part that you're going to make up right here. And this part has these parts, the flat areas that don't bend, and then the bend allowances, and then another area here that doesn't bend. And you want to know what sheet of metal you have to start with. What's the total size of the sheet of metal you have to start with to make this piece? And you know all these dimensions. Let's take a look at the dimensions we do know. And to do that, let's take a look at the top up here and take a look at it. First of all, dimension A is 1 inch. And then we'll have D here and D will give us some information. We'll take a look at D later on. But B here is 3 inches. That's another straight area here. And then we have this curve, and C is 2 inches. Now let's take a look at the information we find out about D and E. All right, first of all, we're going to be given this information in the problem, but D, they're going to have to give you the information you need here, and the same thing for E. So let's take a look at the information they do give you in the problem, and they're going to tell you the setback at D is 0.095, and the setback at E is 0.068. Now that's the setback, and that's where you figure out where to clamp the jaws on and the bend line. And the bend allowance, how much material is used in the bend at D, is 0.150, and the bend allowance at E is 0.112. Now, if we want to figure out how much material is used to make this entire thing, we have to figure out the total distance of A, which is 1 inch, subtract the setback, and that gives us a flat area of A. Then you add the bend allowance. Then you take the total distance of B, subtract the setbacks on both sides, and that gives you the flat area of B, add the bend allowance on both sides, and then C, you take the flat area, and we're going to have to do that by taking the total distance, subtracting the setback, that gives us the flat area, and then, of course, you have this bend allowance here. So let's take a look at it. First of all, let's find the flat area of A. Well, we knew that A started with 1 inch, and they told us that the setback is 0.095, and that's in between A and B. And so you subtract those two, and you find out the flat area of A is 0.905. So flat A here is 0.905. Now, flat B started out at 3 inches, and the setback on the left-hand side is 0.095. The setback on the right-hand side is 0.068, because you have to subtract the setback on both sides if you know the total distance. And here we go, started the total distance up here. Now we're going to arrive at the flat area for B, and you get 2.837. And you have to remember, you have to subtract the setback on both sides there. All right, on C, we start off with 2 inches, and the setback at this point right here, which is E, is 0.068, and the flat area in C is 1.932. So now we got the flat area, so let's figure out the total flat layout. And to do that, we'll take a look at some new figures here. And the total flat layout is the flats A, B, and C plus the bend allowances. And those 2 bend allowances were given to us earlier. And so all we do is take this A, B, and C flat allowances that were flat areas that we figured out, 0.905, 2.837, 1.932, and then we add the 2 bend allowances, and we total all of this up with a calculator, and the total material required to make this entire piece is 5.936. Well, that was obviously too easy for everybody, so let's do another one. And to do that, let's take a look at Figure 6. What we're going to do is try and make this piece of metal that's kind of U-shaped here out of sheet metal. We're obviously going to start off with a piece of flat metal, and we're going to come along here with a straight piece and a bend and another straight piece and a bend, and so on. It looks like this. Now the question is, if you start off with this piece of flat metal, how much flat metal do you have to make this piece with these dimensions? Now they give us a formula up here for setback and bend allowance. Don't let that throw you off. They also actually give you the setback and bend allowance in this particular problem, so we don't have to figure it out. And if we want to know how much material we use, we take these dimensions and find the flat area, the part that does not bend, and you do that by taking the total dimension, subtracting the setback, and they'll give us the setback. So you figure out the flat area, the part that does not bend for A, then figure it out for B, and you have to subtract the setbacks on both sides for B, then figure it out for C. So let's take a look at these dimensions to begin with down here by taking a good close look at it. And the total distance for A is 1 inch. So we're going to take that total distance and subtract the setback that they give us. And for B, the total distance is 2 inches. We'll take that total distance and subtract the setback on each side, because you can see there's a bend on each side. And for C, the total distance is 1.5 inches. We'll take that total distance and subtract the setback, and that'll give us C. Now that gives us the straight areas, the parts that don't bend on each of these. Now we have to find out how much material is going to actually be used in the bend, and that'll be the bend allowance. So you take the flat area, add the bend allowance, flat area, add the bend allowance, and then flat area, and that gives you the total amount of material to make that. So let's see if we can figure this out. Let's take a look at the numbers they give us. First of all, they do give us the distance for the setback, which is 0.252. They also give us the bend allowance, that's the material used in the bend, it's 0.345. So all we have to do is find out each of the flat areas, each of the areas that do not bend. For A, we started off with 1 inch, and the setback is 0.252, so we subtract that. And the straight area or flat area that does not bend for A is 0.748. And then for B, we started off with 2 inches. We have to subtract the setback on each side. It's 0.252, and they're identical. And that gives us a straight area or flat area of 1.496 that does not bend. And let's see if you and I can take a look at it for C at the same time here. C, we start at 1.5 inches, and the setback is 0.252. We only have 1 bend on that particular piece, so it becomes then a flat area of 1.248. Now, all we have to do is add A, B, and C and put the bend allowance in between them. So here's A, 0.748, that's the flat area for A, plus the bend allowance of 0.345. Here's the flat area for B, 1.496, plus the bend area in between B and C, and a flat area for C, which is 1.248. Add all of those together with your electronic calculator, and you get D, which is 4.182, and that is the length of the entire piece of metal you have to start with to make that piece. Now let's take a look at figure 4. Here we're going to make a 90-degree bend, and the question is going to ask you, what is the amount of the material required to make this 90-degree bend? In other words, from the point where the flat ends here and the flat ends here, how much material is there right in that bend? Well, a couple things we're going to need to know to solve this problem. First of all, we need to know the radius of the bend, and it's 3/16 of an inch radius. And we also need to know the thickness of the metal, and it's 0.0625. And we have, son of a gun, the formula for bend allowance right here. They give it to us. They're nice. I can't believe they're this nice. And it's 2 pi times the quantity of the radius plus 1/2 the thickness, quantity closed, all that divided by 4. So that's all there is to it. So let's you and I plug in the numbers and see if we can't solve this problem. I know we can do it. So first of all, we'll start with the formula, and it's 2 pi times the quantity of the radius plus 1/2 the thickness, quantity closed, all divided by 4. And then we'll take 2 pi times the quantity, and the thickness was the radius was 3/16, plus the thickness, which is 0.0625, that divided by 2, and quantity closed, all that divided by 4. So that becomes 2 pi times, and if you use your electronic calculator and divide 3 by 16, you're going to get 0.1875. And you add that to half of 0.0625, and that comes out to 0.03125. You can use your calculator to figure that out if you want to. And now you have all of this divided by 4. And so you continue with this, 2 times pi, which is 3.1416 times 0.21875, and all that divided by 4. And if you use your electronic calculator and do this, it's 2 times this number, all divided by 4, you get a bend allowance of 0.3436, and that is all there is to solving this problem. Now let's you and I do another one, and to do that, let's take a look at figure 5. And what we want to know is the flat layout dimension, the entire amount of material required to make this part. And the way we're going to do that is, of course, we'll take flat A plus flat B plus the bend allowance, and they give us the formula for the bend allowance here, and they give us the setback, which is the radius of the bend plus the thickness, and they give us this dimension. Flat B is 3, the whole amount, not the flat part, but the entire dimension of B here is 3 inches. The entire dimension of A is 4 inches, and now what we have to do is solve the problem. Well, first of all, we need to figure out the setback for A. Let's start with A first. Figure out the setback for A, and that gives us the flat area for A. Figure out the setback for B, and that gives us the flat area for B by subtracting the total dimension, subtracting the setback. Let's take a look at A first of all. First of all, what's the setback? Well, the setback is radius plus thickness. So for A, we start off with 4 inches, so we're going to subtract the setback, and it's radius plus thickness. The radius was 1/4, and the thickness is 0.062. So all we have to do is add those two together. So 4 minus those two things added together, and we'll just here we just converted the 1/4 to 0.250. Then we added them together, and for A, the flat area of A is 4 minus 0.312, or 3.688. So on leg A, this is the part that does not bend. That's the flat area for A. All right, now let's figure it out. We've already figured out the setback, by the way, when we added those two together. And when we figured out the setback is 0.312. So let's figure it out for B now. So let's take a look at the numbers for B. All right, here we go. Flat B is 3 inches, and the setback we just figured out is 0.312, and so the flat area for B is 2.688. That's the part that does not bend for B. Now we need to know the bend allowance, how much material is used in the bend. And we're going to use this formula. We've been through it several times, so all we have to do is plug in the numbers for the formula. It's 2 pi times the radius, the quantity of the radius, which is 0.250, plus the thickness divided by 2. The thickness is 0.062. We'll divide that by 2. And so that's the quantity, all that divided by 4. And now all we did here is we just simply take the 0.062 divided by 2, and it becomes 0.031. So it's 2 pi times the quantity now divided by 4. And well, now let's convert pi to a number, and it's 2 times 3.1416. We add these two together, and it becomes 0.281. All that divided by 4. You use your calculator to figure it out, and the bend allowance is 0.441. So now we've figured out the bend allowance, 0.441. We've got leg A, the flat area, leg B, the flat area, and the bend allowance. All we have to do is add them together. So let's you and I take a look at those numbers when we add them together. And to do that, we have, first of all, flat A, which is 3.688. The bend allowance, which is 2.688, and well, that was actually flat B, I believe. And then we take the bend allowance, 0.441, add them all together, and the total amount of material used in the flat layout is 6.817. And notice, who cares is not a correct answer on any of these questions. All right, now here's a typical FAA type test question about this. The flat layout or blank length of a piece of sheet metal from which a simple L-shaped bracket is made. Now let's assume the L-shaped bracket is 3 inches by 1 inch and is to be bent. Now they're going to ask you how much metal you use depends on what. Let's take a look at some CG for that. How much metal you're going to use depends on the radius of the desired bend. And what you're going to find out, in other words, if you're going to make an L-shaped piece of metal, how much metal you're going to use, how much blank length is required, depends on the radius of the bend. And what you're going to find out is the bracket that will require the greatest amount of material is the one that has the smallest bend radius. Because if you've got a very small bend radius, you kind of go all the way to the end and then go the other direction. Whereas if you have a big bend radius, you can see the bend kind of cuts the corner here. So a small bend radius means you use more material, and they're going to ask you about that on the test. They're also going to ask you, what is a closed angle? A closed angle is one that is less than 90 degrees when measured between the legs, or more than 90 degrees when the amount of the bend is measured. Let's take a look at this drawing here, and I can illustrate what we're talking about. Here's 90 degrees. If you bring this thing and bend it more than 90 degrees, it becomes a closed angle. Now let's assume you brought this thing all the way down and made this angle only 15 degrees. How many degrees would you have to bend it? Well, you start out with a flat piece of metal that's 180 degrees. You bend it around till it's only 15 degrees left. You had to bend it 180 degrees minus 15 degrees. That was the entire amount of the bend. So they're going to ask you, for instance, a piece of flat stock is to be bent to a closed angle of 15 degrees. How much must it be bent? Here's the way you would figure it out. Start off with 180 degrees, subtract 15 degrees. That means you had to bend that piece of metal 165 degrees. All right, let's talk about some characteristics of sheet metal. They're going to ask you some questions about this on the test. First of all, you need to know that clad aluminum alloys are used in aircraft because they're less subject to corrosion than uncoated aluminum alloys. Clad aluminum means it's coated. All right, the aluminum alloys used in aircraft construction are usually hardened by heat treatment. You need to know that. And when they number aluminum, the first digit in an aluminum alloy designation indicates the primary alloying agent. For instance, let's take a look at 2024-T36. 2 is copper. 3 would be manganese, and so on. So the first number tells you what the alloying agent is. Now you can distinguish between aluminum and aluminum alloy by testing it with a 10% solution of caustic soda. Now the alloy will turn black due to the copper if there is copper content in it. So 10% solution of caustic soda tells you the answer to that question. Now here's a question. When you're fabricating parts from Alclad 2024-T3, when you're doing that, What can you do about it? What do you need to do about it? Well, what you need to do about it is make sure that scratches, kinks, tool marks, and nicks must be held to a minimum. They ask you that question. Hold all the scratches, nicks, kinks, and so on to a minimum. If you get a shallow scratch in sheet metal, you can actually fill it in by kind of smashing it back down. That is repaired by burnishing, they call that. Shallow scratches in sheet metal can be repaired by burnishing. Now, let's assume you want to straighten members of 2024-T4. Should you heat the metal up to straighten it? And the answer is no, you should straighten it cold, because you can change the strength of the metal. It loses the strength when you heat it up. So you straighten it cold and then reinforce as necessary. But they don't want you heating up 2024-T4 to bend it. They want you to straighten it cold. All right, now let's take a look at some things that you need to know. First of all, can you repair aircraft structural units such as spars, engine supports, and so on that have been built from sheet metal? And the answer is yes, provided you use approved methods. If you want to make a repair to sheet metal, you must use approved methods. Now, they also ask the question, let's assume you're repairing a small hole on sheet metal stressed skin. What is the major consideration when you're designing a patch for a small hole? Let's assume you had a hole and you're designing a patch for it. What is the major consideration? And the answer is the shear strength of the riveted joint. You need to know that riveted joints are subject to shear, not tension. They're not being tried to be pulled apart. There's shear loads are on them, and it's the shear strength that you should take into consideration. All right, let's take a look at another one. Repairs or splices involving stringers on the lower surface of the wing are more critical to, in reference to tension than the upper surface. That makes sense. The lower part of the wing is being pulled apart. The upper part of the wing is being squeezed together. So repairs on the lower surface are critical in regard to tension. All right, they're also going to ask you, what is the purpose of a gusset or a gusset plate? Well, a gusset or a gusset plate is used in the construction and repair of aircraft structures, and there's a great example right there, to join and reinforce intersecting structural members. You'll see gussets very often in wood construction. Now let's take a look at forming operations. Let's assume you want to form a streamlined piece of metal. Now here we're going to talk about forming it with a vengeance, but in general, the way you form a piece of metal is you have a mold and you would pound into that mold. Well, let's assume on the FAA test they ask you about a streamlined cover plate. So you're forming a streamlined cover plate, you're hand forming it using a form block. You're pounding it in there. And you should use a piece of dead soft aluminum. You first place it over the hollow portion of the mold and then securely fasten it in place. And then you begin what is known as a bumping operation. And you do that by tapping the aluminum lightly around the edges and gradually work in towards the center. So if you're trying to form a piece of metal, they say start tapping around the edges and work into the piece of metal. Now, afterwards, you can use a concept called annealing of aluminum, and that removes stress caused by forming. And so the question is, what is annealing? And annealing is heat treating the metal, and it removes stress caused by forming. They're also going to ask you, what is a joggle? And a joggle is an offset formed on an angle strip. And what it is, you're going along like this, and all of a sudden there's a joggle. And it's an offset like so, and that is called a joggle. That's just a question they want to ask you in the test, is to allow clearance for a sheet or an extrusion. So that's called a joggle. We'll talk more about that later on. Now let's cover what I think is a painful subject, and that is drilling and reaming. And they're going to ask you some questions about drills, and they want some definitions and terms. First of all, they ask you, what is the flute of a drill? Well, the flute is the grooved portion here in the drill, and the land is the raised portion. They also ask you, what forms the cutting edges of the drill? Well, here at the point, the cutting edges are actually formed by the intersection with the flute with the land here. But that's not the way they put it on the test. They make you choose between the flute and the land. And so the correct answer on the test is the flute section of a twist drill forms the cutting edges of the drill point. Now, I think it's a stupid question, but the FAA never asked me about these questions anyway. All right, they're going to say, let's assume you're drilling soft metals. What kind of included angle should you have at the drill bit? Well, the included angle is the angle from vertical down to here. So here we had vertical, and so the included angle for soft metals is 90 degrees. And it's from vertical to this direction right here. So here's the angle for half of it, and the other half makes the total included angle here. 90 degrees for soft metals, hard metals 118 degrees, and stainless 140 degrees. So you and I have got that figured out. Now, when you are drilling stainless steel sheet, as we said, the drill should have an included angle of 140 degrees. And when you're drilling stainless steel, the drill should turn at a lower speed and with more pressure applied to the drill than you would if you're drilling aluminum alloy sheet. So stainless steel, an included angle of 140 degrees, low speed, and a little more pressure. Now let's assume you're using a reamer to finish a drilled hole to the correct size. What you need to know is that you should only turn the reamer in the cutting direction. Do not turn it in the other direction. You might cause damage to the reamer and to the hole. So make sure you turn the reamer only in the cutting direction. Now let's hold things together with rivets. And what the FAA wants you to know is that the rivets have numbers, dash numbers at the end, and they tell you the dimensions of the rivet. For instance, the diameter of the rivet is the first number, and it's here -4, and it tells you the diameter of the shank in 30/2 of an inch. So the first dash tells you the diameter of the shank in 30/2 of an inch, and how about that second dash? Well, the second dash tells you the length of the rivet in 1/16 of an inch. Now, if you're working with a countersunk rivet, it's the overall length of the rivet, but if you're working with another kind of rivet, it's just the length of the shank. So the second dash tells you the rivet length in 1/16 of an inch. Now, do you think they might ask you a question about this? You bet they will. They're going to say, what are the dimensions of a MS-20 430AD-4-8 rivet? Well, the -4 tells you it's 4/32 or 1/8 of an inch in diameter, and the -8 tells you it's 8/16 or 1/2 inch long. Let's do another one. Let's assume this time you're working with an MS-20 426AD-6-5 rivet. That happens to be a countersunk rivet, and they're going to ask you what's the overall length of that rivet, and the second dash tells you it's 5/16 of an inch long, and that is the answer to the question. So these little numbers, particularly the dashes at the end, have great meaning for you. All right, now how do you identify the alloy of a rivet? Well, you notice that there are identifying marks on the heads of aluminum alloy rivets. They indicate the specific alloy being used. So you see these marks here, and they tell you the specific alloy being used. A dimple on a rivet, or as they say in the test, a single recessed dot, identifies a 2117-T field rivet, 2117-T field rivet. That's the kind of rivet, by the way, that's used more than any other aluminum alloy rivet for riveting. All right, now let's take a look at making wing skin repairs. What precautions should you use? And the answer is you should use rivets, and this is always true, not just in wing skin repairs, but anytime you make repairs, rivets should be of the same alloy as the material being riveted. You wouldn't want to use a different alloy. For instance, mild steel rivets are used for riveting steel parts. Monel rivets are used for nickel steel alloys, and an aluminum rivet is used for riveting magnesium alloys. You want to make your own battery? You can do it very, very easily. All you have to do is put two dissimilar types of metal together, and it creates a battery. And anybody that's been around mechanical things knows that when you have a battery, very often you have lots of corrosion. Well, sometimes when you're putting airplane parts together, you have to put dissimilar metals together. You have to rivet them together sometimes, and that sets up corrosion. It would be wise if you could avoid doing that, but sometimes the airplane is made of two different types of metals and you have to put them together. That's all there is to it. So when you do have to rivet two dissimilar types of metal together, what you should do is place a protective separator between the areas of potential electrical difference. And when you do that, you keep those two dissimilar metals separate from each other. The separator could be, a thin gasket or aluminum tape or cellophane or impregnated fabric. But the thing to remember is keep those two dissimilar metals apart with a protective separator, or else you've got yourself a battery. Now take a look at this. At first blush, I'll bet you think that that is a rivet. Well, It is, but on the FAA written exam, they will also call it a hole-filling fastener. And the FAA wants you to know that hole-filling fasteners like this rivet should not be used in composite structures. Now we're talking about fiberglass or Kevlar. And the reason is when they are bucked, they can expand against the sides of the laminate of the composite structure and cause delamination at the edges of the hole. So they expand and damage the composite. So you should not use hole-filling fasteners on composite structures. How about that? Now let's talk about shear strength of rivets. Shear strength is this kind of strength, so the rivet doesn't get sheared off, and it's important. That's the kind of load you put on rivets, and it's important to know that a rivet sometimes is not as strong as it's going to be when it's first installed. They're going to ask you about an MS-20 470D rivet. Now what this is a heat-treated rivet, and you actually store these rivets cold and they harden when they get hot. And so you store this cold, you put it in, it hardens over time, or you heat treat it when you put it in, but it doesn't get its full strength until it's spent about 4 days at room temperature, then it gets its full strength. That's a MS-20 470D rivet. It's a heat treated type of rivet, and the FAA wants you to know that it's going to take a period of age hardening, about 4 days before it gets hard. Now, under certain types of conditions, another kind of rivet, an A rivet, should not be used. Why should you not use an A rivet? Well, they are 99.45% pure aluminum. You'd think it'd be 99.44% pure, but it's even a little more pure than ivory soap. So these are 99.45% pure aluminum. That's type A rivets, and you should not use them in certain cases because they just won't be strong enough. Now let's cover some real riveting information. I'm sorry I had to do it about rivet layout. They're going to ask you a few questions about rivet layout, and we're going to use this old Ford tri-motor here to illustrate this. Rivet pitch. What is rivet pitch? Well, rivet pitch is the distance between the centers, we're talking about the center of the rivet, of adjacent rivets in the same row. So this is rivet pitch, the distance between the centers of the adjacent rivets in the same row. I don't see why they say words like adjacent. I guess the rivets next to each other is what they're trying to say here. What is the factor which determines the minimum space between rivets? And the answer is the diameter of the rivets determines the minimum space between rivets. And rivet length, by the way, should not be considered when you're determining that minimum rivet spacing. It's the diameter of the rivet. So minimum rivet spacing or pitch for a single row of aircraft rivets is 3 times the diameter of the shank. And the minimum edge distance is 2 times the diameter of the shank. That's how far you can get from the edge of the piece of metal. So the pitch, that's the spacing in between rivets, is 3 times the diameter of the shank. Minimum edge distance 2 times from the diameter of the shank. And of course, you're going to need to know this. Now here's an example of how this information will be helpful to you when you answer an FAA test question. They say, let's assume that you're using a type of rivet which is an MS-20470 AD-4-6 rivet. And what you're going to do is you're going to rivet a plate to something else, which is 10 inches by 5 inches. And you're going to use a single row of rivets all the way around here like so. And you're using a minimum edge distance, the minimum edge distance allowable, and 4D spacing. What's 4D spacing mean? Well, it's 4 times the diameter of the shank of the rivets is what 4D spacing means. Now, minimum is 3D, but we're using in this case 4D spacing. All right, now let's take a look at it. First of all, the diameter of the rivet is 4/32 or 1/8 of an inch. If we're using minimum edge distance, which they told us they're using, then we're going to use 1/4 of an inch, 2 times the 4/32, which is 1/8. So we're going to have 1/4 of an inch all the way around, and that means the actual dimensions will be cut shorter. Instead of having 10 inches, we're going to have 1/4 off each end, or 1/2 inch off the total distance there. So let's take a look at the numbers and see what we're going to get as the dimensions to work with. Instead of that 10 inches, we're going to subtract that 1/2 inch, and that gives us 9.5 inches. And for this dimension, we're going to have an edge distance 1/4 on each side for 1/2 inch, so it becomes 4.5. So now we have 4.5 by 9.5 inches. And the total perimeter, one side is 4.5 by 5, and the other 2 sides is 4.5 by 9.5, and so that's a total of 28 inches around. Now they told us we're going to use 4 times diameter spacing. Well, 1/8 of an inch is the diameter of the rivet shank right here, 4/32. So 4 times that would be a 1/2 inch spacing. So instead of 28 inches, now we have 2 rivets per inch because we're using a 1/2 inch spacing. So you multiply that times 2 and it's going to require 56 rivets to do this all the way around. So we use minimum edge space, which is, in this particular case, what we did is we doubled the rivet diameter to find minimum edge space. And we also use 4 diameter spacing when we solve the problem. Now, another concept we need to know about is transverse pitch, and that's the distance between rivet rows. The minimum transverse pitch is 75% of the pitch. You can guess we're going to need to know that. So let's take a look at a drawing and see if we can make some sense out of it. Here's the drawing, and here's the transverse pitch right here. It's the distance between the rows. All right, now here's a question. A single lap splice is to be used to repair a section of damaged aluminum skin. Now, if a double row of 1/8 inch rivets is used, what is the minimum allowable overlap? All right, let's take a look at the question. First of all, we're going to have 2 rows of rivets, and the question is, you have an edge distance and you have transverse pitch. What is the minimum amount you can overlap this lap splice? And lap splice is just one piece of metal laying over the top of the other like so. So what is the minimum amount of overlap? Well, what we're going to do is we're going to figure the edge distance in each case, and we're going to figure the transverse pitch. That's the pitch between the rows. All right, now do we know what kind of rivet we're going to use? Yes, we're going to use a 1/8 inch rivet. So what is the edge distance? Well, it's 2 times the diameter. We're using 1/8 inch rivets, so the edge distance is going to be 1/4. We know that. And we also need to know the minimum pitch between the rivets. Well, the minimum pitch should be no less, generally between the rivets, no less than 3 times the diameter. So let's figure out that by looking at some numbers here. First of all, the edge distance, we already figured out it's going to be a 1/2 inch, so 2 1/4 inches. The pitch, the minimum pitch between rivets themselves is 3 times the diameter of the rivet. They were 1/8 inch rivets, so that'd be 3/8 of an inch. Now, the transverse pitch, the distance between the rows, is 75% of the pitch, or 3/4 of 3/8, and 3 times 3 is 9, and 4 times 8 is 32. It's 9/32. So the transverse pitch, the distance between the rows, the minimum distance is 9/32. The minimum overlap, then, is going to be the total edge distance plus the transverse pitch. And so the total edge distance is 1/2. The transverse pitch is 9/32. So 1/2 becomes 16/32 plus 9/32 is 25/32. So what's the minimum overlap? 25/32. Now, they don't give you 25/32 as an answer on the test, so the correct answer on the test is 1 inch. Of course, the whole idea of riveting is to rivet sheets of metal together, so they're going to ask you some questions about the rules involved in doing that. First of all, the general rule for finding the proper rivet diameter is 3 times the thickness of the thickest sheet. So you take the thickest sheet, multiply that times 3, and that's your rivet diameter. Now, when you want to determine the total length of the rivet, the combined thickness of the materials becomes important, and that is called the grip length. Now, they're going to ask you a question on a test about grip length, so let's take a look at figure 3 here, see if we can answer that question. First of all, the thing to remember, that grip length is the total length of the material. So it's not the total length of the rivet, it's not part of the material, it's the length of the material. So which one of these is the grip length? 1, 2, or 3, and the correct answer is 3. The grip length in this particular case is 3. Now, what is the total length of the rivet? What should it be? And the answer is, when you're installing a rivet, the total length of the rivet should be equal to the grip length plus 1.5 times the diameter of the rivet shank. Now, do you think they might ask you a question about that on the test? You bet they will. They're going to give you 2 pieces of material you're going to join together, 32 thousandths and 64 thousandths, and they're going to ask you, what should the rivet length be? Well, it should be the grip length, which is the sum of those 2, which is 96 thousandths there. And the rivet length should be that grip length plus 1.5 times the shank diameter. And so it's 1.5 times the rivet diameter plus 96 thousandths in this particular case, and that's the way they give you the answer on the test. Now let's do another one. This time they'll say, what's the length of the rivet to be chosen when making a structural repair that involves joining a 32 thousandths and a 64 thousandths piece of material? Well, that's the same material we had earlier. The total grip length then is the total of those two, 96 thousandths. And the rivet length should be 1.5 times the shank diameter. And in this particular question, they will tell you that you're going to use a number 30 drill. Now, what will you do in real life if they tell you that you're going to use a number 30 drill? You'll look it up on a table, and that table will tell you that a number 30 drill uses a 1/8 inch diameter rivet, and that's all there is to it. Now, let me ask you a question. Do you think that they will give you this table on the test? No, you're going to have to remember that a number 30 drill will take a 1/8 inch rivet. That's all you can do, is just remember it. So now what you want to do is multiply that 1/8 of an inch times 1.5. Let's see, 1/8 is 2/16. So if 50% more would be 3/16. So the 3/16 is the figure of 1.5 times 1/8. So now you have 3/16, and you're going to add that to your grip length. Well, 3/16, by the way, is 3 divided by 16. You can use your electronic calculator, and you get 0.1875. So the rivet length is that grip length of 96 thousandths plus the 0.1875, and the closest you can get is 0.2835, and the closest rivet length would be more than a quarter. That's 4/16. It's going to be 5/16, and that's the rivet you would use. And by the way, if you have a number of like 0.2835 you want to get, and 5/16 is all that's available, you can actually trim that rivet a little bit. But on the test, the correct answer is 5/16 of an inch. Let's do another one. They're going to ask you, which rivets would you select to join two sheets of 32 thousandths aluminum? Well, the proper diameter of a rivet is 3 times the thickest sheet. 3 times the thickest sheet would be 3 times that 32 thousandths, or 96 thousandths. So the diameter is 96 thousandths. And the closest you're going to come to that is 4/32. You can use your calculator to figure it out, because you know that rivet lengths, rivet diameters are in 30 seconds. So 4/32 comes out to 0.125 diameter. And so the closest you're going to have here is a 4/32 rivet. Now, how about the length? Well, the length is 1.5 times the diameter plus the grip length. The grip length is twice this material because we have 2 sheets. The grip length is 2 times 32 thousandths, and so that comes out to 64 thousandths. And the diameter is 0.125. You want 1.5 times that, and that comes to 0.1875. So you add these two numbers together, and now you have 0.2515, and that comes to 1/4 of an inch. And a -4 rivet, which is 4/16, is the correct length of the rivet. 0.250 is what you get right there. So that's all there is to it. You're going to choose a -4 rivet. All right, let's do another one. Let's assume that you have a sheet metal repair to be made using 2 pieces of 40 thousandths inch aluminum, and they're going to be riveted together. All right, and all rivet holes, by the way, are drilled for 3 32 inch rivets. What length of rivet should be used? Well, the length, as you remember, is the grip length plus 1.5 times the diameter. The grip length would be 2 times those 40 thousandths sheets you're going to have, because you're going to have 2 of them together, and that would be 80 thousandths. You see that right there. And you want 1.5 times the diameter. The diameter is 3/32. You can use your calculator, take 3/32, divide 3 by 32, and you get 0.09835. 1.5 times that gives you 0.141. So you take the 80 thousandths plus 0.141, and you get 0.221. Now the problem is, when you go out to buy a rivet, if you ask the man for a rivet that's 221 thousandths of an inch long, he's going to look at you like you're crazy, because rivets don't come in increments like that. They come in increments of 1/16 of an inch in length. So you can get one that's 1/16, 2/16, that'd be an 1/8, 3/16, or we'll make it 4/16, that'd be 1/4 of an inch long. And so in this particular case, you want a rivet that's 1/4 of an inch long. Now let's talk about installing this rivet in the aircraft. Well, one of the things you might consider doing when you install a rivet, and let's take a look at figure 2 to do this, one of the things you might consider doing is making the rivet flush with the skin so that it doesn't stick out and create aerodynamic drag. Well, a way you can make it flush with the skin is to countersink the rivet so the rivet is actually inside the metal. You could do that by dimpling the airframe a little bit, and that is actually one method of doing it. But the other method of countersinking a rivet is to machine a hole for the rivet or drill a hole for the rivet, and that's called machine countersinking or drill countersinking. So let's assume that you want to make a countersink a hole for countersinking a rivet. What is one of the determining factors on whether or not you can do that? Well, one of the determining factors is the thickness of the material. You want to make sure the thickness of the material is greater than the rivet head. If you don't do that, you won't have any gripping surface there. So in case 3, you can see that the countersinking went right through this thickness of this material. Same way in case 2, went clear through it. Case 1 is the preferred method for countersinking rivets because the rivet head, the countersunk part, did not go clear through the thickness of the material, and there's plenty of room for gripping. So if you look at figure 1, they're going to ask you on this question, which is the preferred method of countersinking, and the answer is answer 1 here. And the reason is that the countersinking doesn't go all the way through the thickness of the material, and there's plenty of room for gripping. Now, when people talk about a countersunk rivet, one of the things they talk about is how many degrees of countersunk does the head have to it, or countersink, I guess you might say. Here's an example of a 100-degree countersunk rivet. What we're talking about is not this angle, but this angle right here. And if you take 130 plus 130, that comes out to 260, and there's 360 degrees in a circle, so obviously you can see what's left over is a 100-degree countersink. So they're talking about them from this line to this line is how many degrees of countersink that you have. Now, they're going to ask you a question about that on the test. So let's take a look at figure 1 here, and you see 3 situations, and the question they're going to ask you is which of these is a 100-degree countersunk head? Well, this is an 80-degree countersunk. This is something different. This is 50 plus 90, 140 here. Well, 100-degree was this situation we talked about earlier. Here's 130 here, 130 there. There's 260, and that leaves a 100-degree countersunk head. So which one of these is a 100-degree countersunk head? And the correct answer is number 1. Let's talk about driving rivets. And one of the things you need to know is that almost all rivets, one way or the other, are heat treated. For instance, a 2117T3 rivet is heat treated by the manufacturer. It does not require heat treatment before it's driven. It can be used as received without further treatment. On the other hand, some rivets in the field require heat treatment right there in the field before you use them. A good example is a DD rivet is heat treated before being used in order to soften it, and then you put it in the refrigerator. Believe it or not, if you're not going to use it right away, you put it in the refrigerator. And the purpose of refrigerating either D or DD rivets, and there's either 2017 or 2024 rivets, is to retard age hardening. So you field heat treat them, put them in the refrigerator, and then it retards the age hardening. Now, if you have a D or a DD series rivet and they're not driven within a prescribed period of time, they gradually get harder and you're going to have to heat treat them again before you use them. Now, they ask you a question on the test about driving an AN 470 rivet or an MS-20 470 rivet, and they say, what kind of rivet set should you use? And the answer is the rivet set should have a slightly greater radius than the rivet head itself. Also, they ask you about a high shear rivet. Those are very strong rivets, and the way a high shear rivet works is you crimp or swage this collar into a groove. They want to ask you what happens if a high shear rivet is underdriven. And the answer is the collar will not be completely swaged into the groove. You're not going to get it in there properly if it's underdriven. Now, I want to talk about something that you already know about rivets. Are you ready for this? Rivets have 2 ends. There's the manufactured head that comes from the manufacturer, and that's the way the rivet comes, with the shank and the manufactured head. And then there is the bucked head or the shop head, the head that you create in the shop. Now, when you create this, you do it by driving the rivet, holding a bucking bar against it, and the rivet spreads out and you create a shop head. Now the question is, how big should that shop head be? And it should be at least 1.5 times the diameter of the rivet shank. So this diameter should be 1.5 times of that diameter. And that's how you buck a rivet, and that's how you create the shop head, and that's the dimensions. It should be 1.5 times the diameter of the rivet shank. Now let's take a look at inspecting rivets. First of all, what does a well-designed rivet joint look like? Well, a well-designed rivet joint will be subject to shear loads. It's shear loads that rivets are designed to take, not tension loads that pull them apart. And shear loads then are the cause of most failures on rivets, and the reason for that's the kind of load they take. So that's what's going to cause the failure is shear loads, cause rivet failures. Now what happens if you pull a rivet out and look at it and you see a joggle? I told you we're going to get back to joggle. If you see a joggle in the rivet, in other words, a rivet does this, and that means you had a partial shear failure. It joggled the rivet over. So a joggle in a rivet indicates a partial shear failure. Now let's assume you're inspecting the stressed skin metal wing assembly, and it's known to have been critically loaded. Now, how would you know if a skin assembly has been critically loaded that you've got a problem? Well, a genuine rivet tipping has occurred if groups of consecutive rivet heads are all tipped in the same direction. In other words, if all the rivets are tipped in the same direction, then you have genuine rivet tipping and you have deep troubles. Now let's assume that you are inspecting an aircraft and you happen to notice some black smoky residue. Sometimes it streams back in the airstream behind a rivet. What would that tell you? Well, that would tell you that you have fretting corrosion, because that is what is known as a working rivet. It's moving around in there, and actually corrosion is occurring because it's rubbing around and you're getting corrosion between the rivet and the skin. That's called fretting corrosion because it's actually just simply little pieces of rivet and skin going away, and it's a very bad deal. So that's one of the things you want to look for is black smoky residue when you are inspecting an aircraft, and it's a working rivet and you need to replace it. Now let's talk about removing rivets. Let's assume you do want to remove a rivet. Generally the best procedure to use when you're removing a solid shank rivet is to drill the base of the manufactured rivet head with a drill that's just one size smaller than the rivet shank, and then remove that rivet with a punch. Let's talk about specialized rivets. Let's assume that you make a repair and you can't get in there to buck the rivet. What would you do? Well, you would install what is known as a blind rivet. A blind rivet can be installed from one side. You don't have to buck the rivet. It actually pulls through and tightens up. Now, two types of blind rivets are Cherry Max and Olympic lock rivets, and they utilize a pulling tool for installation, and you just simply pull the rivet through and it expands out and tightens up. Now let's assume you want to attach something to a piece of sheet metal with a screw. How would you do that? Well, you could install what is known as a threaded rivet, or more commonly called a riv nut. And it's simply a rivet that has threads on the inside of it. Let's take a look at how it's going to look in an airplane. Here you have sheet metal, you've drilled a hole, shove this rivet through, the rivet has threads in it, then you pull the rivet tight with the threads, with a special tool here, and now you have a tight rivet with threads at the bottom, and you can drill or screw a bolt into that, and now you can attach something with that, and that is called a riv nut. So riv nuts are used to attach parts or components with screws to sheet metal. Now let's assume you're building yourself a very big airplane and you have need for very strong fasteners, fasteners that are stronger than solid shank rivets. Well, then you might use special fasteners such as high shear, high lock, lock bolt, or huck bolt type fasteners. We'll talk about these. First of all, high shear was the first generation. Another generation later down was a high lock fastener. Now let's take a look at a high lock fastener. It's one of a type that has a sealing collar that's threaded onto a pin, or what is known as a threaded structural pin right here, and you can actually use hand tools to screw this collar down tight, and it makes a very strong fastener. Now, one of the main advantages of high lock type fasteners is that they can be installed with ordinary hand tools. So high lock fasteners, hand tools, very strong, very light. The thing you need to remember is that high lock fasteners, you can use hand tools on them. Now, conventional fasteners, you cannot use hand tools. They're called lock bolts, conventional lock bolt fasteners. There's two types. There's both a lock bolt or a huck bolt, and they're both the same thing, but you cannot use hand tools. You use a pulling tool with these. And there's also two types of lock bolt or huck bolt fasteners, tension and shear types of fasteners. And what you can do is determine the difference between tension and shear fasteners by looking at the number of locking grooves in the collar here. If it's a shear type fastener, it'll have 2 grooves. It's a tension type fastener, it'll have 5 grooves. And the thing you need to remember is you can tell the difference between these two by counting the grooves. Let's take a look at a totally different kind of fastener. What's the use? Let's talk about a Zeus. Here's a Zeus right here. A Zeus turn lock fastener consists of 3 parts. Let's take a look at those 3 parts. First of all, you have a stud, you have a grommet, and you have a wire receptacle for it. So here's a stud, then you have a grommet that goes around here, and then you have a wire receptacle. And those are the 3 parts of a Zeus turn lock fastener. Now the markings on the head of a Zeus fastener identify 3 things. First of all, the body diameter, the type of the head, and the length of the fastener. They don't ask you how to read these things. You just need to know that you can find out the body diameter, the type of the head, and the length of the fastener by looking at the markings on the head of a Zeus fastener. How is stud length measured? Now we're talking about Zeus's still, and the answer is in hundredths of an inch. Stud length is measured in 1/100th of an inch. Stud diameter, still on the subject of Zeus's, stud diameter is measured in 1/16th of an inch. Now let's talk about nuts. And no, we're not talking about my personality here. We're talking about this kind of nut. A cotter pin is an acceptable safety device, they say, for a castle nut when it's installed on secondary structures. So if it's not a primary structure or it's on a secondary structure, a cotter pin is an acceptable safety device. Now when a fiber stop nut can be threaded on a boulder stud with just your fingers, if you can twist this big fiber nut on with just your fingers, it should be replaced because it's not going to work as a stop nut. Now let's assume you're building something with a carbon graphite composite structure. Now the question is, can you use metal fasteners with a carbon graphite composite structure? And the answer is yes, you can, if the fasteners are titanium or corrosion resistant steel. Now you have another alternative of dipping the fasteners in a barrier like epoxy, but the test answer is any metal fasteners that are going to come in contact with carbon graphite composites must be titanium or corrosion resistant steel. Now let's talk about composite structures, often referred to as bonded structures. I think of bonding as gluing something together, but they're called composites. So let's take a look at composite structures. And composite structures very often are made of plastic resins reinforced with fabric. And the types of fabric you could put in there as reinforcement could be fiberglass, aramids, which is Kevlar, filaments of carbon or boron, and that fabric goes inside the resin. Now the fiber to resin ratio for advanced composites, what they call wet layups, is generally considered to be 60-40, and that's fiber to resin, and that gives you the best strength. Now the resins are the matrix or the bonding material which completely surrounds the fiber. And here you have the fiber, here you have the resin going on, and that resin completely surrounds the fiber. Now the resins come as a 2-part system, resin and catalyst, and they have to be mixed in the proper proportions. And resins actually have inhibitors, and these are used to slow down or retard the hardening process. And a catalyst is used to actually suppress the inhibitors. And what causes the molecules to join or solidify is heat. And so you have an accelerator combined with the catalyst, and that creates heat. Now, accelerators can be pre-mixed with the resin by the manufacturer or added to the resin later, but you never add the accelerator to the catalyst alone because you might have a little bit of smoke in a room if you do that. Now, there are actually 2 types of resins. The first type, the one we all started with, was polyester resins, and they're used with fiberglass. They're not quite as strong as the more modern resins, and they're used for many non-structural applications. So we started with polyester resins. Then later on, we went to epoxy resins. Now, epoxy resins have a lot of advantages: low shrinkage, high strength to weight, high resistance to chemicals, high adhesiveness to most materials. So the more modern system is epoxy resins. Now, let's assume you're mixing up a batch of resin. What you want to do is mix enough extra materials for a test sample. And you can use that on an identical layup on a piece of scrap. And the test sample will indicate the cure time needed as well as the physical characteristics of the layup. So make enough extra to do a test sample. Now the length of time a catalyzed resin like this will remain in a workable state is called the pot life. Now let's talk about the structural fibers that are used in composite construction. There's really basically three types we want to talk about: glass fiber, aramid fiber, which is Kevlar, and carbon graphite fiber. Now there are more types. You could have boron and so on, but these are the most common. Let's talk about glass fibers. Now glass fibers look like this. There are basically two types. We'll talk about those, but glass cloth, which is referred to as fiberglass, has a tremendous advantage in that it is almost impervious to everything. It's cheap, it's available, and moisture and mildew and chemicals and acids all have no effect on glass fabric. Now the two types of glass fabric, first of all, is E-glass, and this is E-glass that we have right here. And E-glass is the type that's used most commonly because it's cheapest, and it has an advantage, and the advantage is high electrical resistivity. In other words, it does not conduct electricity very well. Now on the other hand, a little more expensive is S-glass, and it is a lot stronger. It has what they call high tensile strength, and you would use S-glass where you need a real strong structure like in the wings of an aircraft, then you'd use S-glass. Now if you want to spend even more money, you could go to aramid fiber, which is referred to as Kevlar, and it has the advantage of high tensile strength and lots of flexibility, but the disadvantage is it costs even more. Now another kind of material you could use is carbon graphite fiber, and it has the advantage of a lot of stiffness, high compressive strength, and it has the disadvantage that it's corrosive when it's in contact with aluminum. Now let's talk about some details of composite construction. First of all, the strength and stiffness of a properly constructed composite buildup depends primarily on the orientation of the plies to the load direction. Now when you're talking about cloth, there are two directions that thread can run. First of all, there's the warp direction, and this has nothing to do with warp drive, and the fill direction. Now the threads of the warp direction of a cloth run along the direction as it comes off the bolt of fabric. It's a long threads, and the fill direction are the cross-woven threads. So here is the warp direction, and here is the fill direction. Now there are more threads woven in composite fabric material in the warp direction than in the fill direction. So there are more threads here in this warp direction, and therefore the warp direction is considered to be the strongest direction. Now let's assume that you're making a repair. Well, if you're going to make a repair, you want to make sure that you have the plies of fabric lined up properly in the direction that they were originally. For instance, you might have the warp direction one time going this way, another time 45 degrees to the right, another time 45 degrees to the left. And you want to do all that correct. So you are going to use a device that looks like this. No, this is not a snowflake. This is what is known as a warp clock or a warp compass, and it's a reference tool used to determine how the fiber will be oriented for a particular ply of fabric, and you would do that when making repairs. Now let's assume you are making a repair to a composite structure. You might use what is known as a vacuum bag pressure system. Now a vacuum bag pressure system uses air pressure to put pressure on the repair, to shove everything down and make it tight. What you do is make an airtight system and actually use a vacuum pump and pull the air out of it, and all these layers get pressed down on it, and that puts a lot of pressure on it, and you're using the atmospheric pressure to help you out. Here's the man sealing it tight, making sure the whole thing is tight, and when you get done, you're going to suck the air out of it, and that air pressure puts pressure on it, and you can have a heat blanket in there to get things warm at the same time. So that's a method of putting pressure on and keeping it on for a long period of time when you're doing a repair. Now here's what the system looks like in detail. First of all, you're trying to do a repair, and here's the repair material right here. The next layer will be a layer of plastic called release film, and what this does, it's actually called, it's called release film. It has little perforations in it, and any excess resin can get through here and go into what is called the bleeder, and the bleeder absorbs the excess resin. It's kind of like a piece of felt or something that absorbs the excess resin, and then you can have some pressure blankets on here and a heat blanket, and finally you got the vacuum on top that presses the whole thing together. Now they're going to ask you on the test, what is the material called to absorb the excess resin? And the answer is that's the bleeder. It's a felt type kind of material, kind of like a blotter that absorbs the excess resin, and that's called the bleeder. And then you have the perforated release film underneath that. And the reason you don't use the bleeder right onto the repair is it'll stick to the repair. You use the release film to keep things from sticking, and the perforated release film allows the excess resin to go through the holes and into the bleeder. Now, sometimes when you're doing a repair, you might make your life simpler. Instead of making your own materials, just to buy materials already impregnated with the matrix, and that is what they call pre-impregnated fabrics, or pre-preg. And they've been dipped into a pre-mixed resin solution and dried and rolled and refrigerated, and the refrigerator slows down the catalyst reaction. So you keep it in the refrigerator, you pull it out and apply heat to it, and then it begins to cure. Now, the proper curing is generally accomplished by applying some kind of pressure on it and some kind of heat. You might use a vacuum bag pressure system like this, but you cure it by applying pressure and heat. Here we have a heat blanket in here, just an electric blanket basically for the purpose, and applies the pressure on it. Now let's assume you have a piece of composite material and you would like to change the shape of it by doing a little milling to it. And you can actually use a fluid to mill under very high pressure. And the question is, what kind of fluid is acceptable to mill composites? And the answer is there's only one fluid acceptable as a cutting fluid to mill composites, and that fluid is water. Now let's talk about inspecting composites. And one type of composite might be a fiberglass laminate like this. And let's assume that you think there might be some internal damage. Well, one of the things you can do is actually shine a strong light through it. But first, what you need to do is strip the damaged area of all paint and get it completely clean, and that's what she's doing right here. Then shine a strong light through it, and you can see the extent of the damage. So a light would be one way of inspecting composites, particularly a fiberglass laminate. You might have fiberglass, a foam core, and fiberglass, and you could actually get a light through that and see what's going on. Now here's a very sophisticated piece of test equipment. It is a coin, and you can use it to tap on a composite structure, and you should hear a ring. If instead you hear a dull thud, it might mean that you have separation of the laminates. So that would be an indication of that, and that is what is known as the ring test or the coin tap test. And if you do locate a separation of the laminates, then what you need to do is determine the extent of the separation by other inspecting methods, possibly including opening up the structure and looking inside. That'd be a lot of trouble, but that's what you need to do. Now here's another inspection method known as acoustic emission monitoring, and it almost sounds impossible, but what you do is listen to the noise of corrosion. You employ or make use of a microphone, a very sensitive microphone. You place it on the surface of the bonded structure, and then you have an amplifier. And if active corrosion is present, the noise associated with the bubbles generated by the corrosion activity can actually be detected as a hissing sound. Now, if you heat up this structure to about 150 degrees Fahrenheit, you can also hear the disbonding of the adhesive with a cracking sound. So they're going to ask you about this on the test, and this whole process is called acoustic emission monitoring. Now, we just got done inspecting composites. Let's see if you and I can figure out how to repair composites. And the first thing to do is make sure you get the area clean so you'll get a good bond. And they're going to ask you on the test, what should you do your final cleaning with? And the answer is you should use MEK, and that is short for methyl ethyl ketone. Of course, if you use this, never read that warning. It'll scare the daylights out of you. Now let's assume you have some superficial damage to fiberglass. Let's assume that you have some scars, scratches, surface abrasion, or rain erosion, and you want to repair it. Well, one of the things that you could do is apply one or more coats of suitable resin. Just simply apply it right to the surface, and you would want to make sure that you use the resin that was room temperature catalyzed so it would harden at room temperature. Now let's assume that you have a fiberglass laminate, we'll say consisting of fiberglass, some high-density foam core, and some more fiberglass, and you have damage just to the first layer. It does not exceed the first layer of ply. How can you repair that? Well, what you can do is fill it with a putty consisting of a resin and clean, short glass fibers to add strength. Now, short fibers or chopped fibers are referred to as flocks. And this is an example of flocks here. You can add flocks to a wet resin anytime you're making a repair, and it improves the strength. Let's assume, for instance, you have a composite structure and you have damaged fastener holes. You would add flocks to the resin, and that'd just make it a little stronger. What you do not want to add to the resin we have here on the right, because on the right we have microballoons. And microballoons act as a filler, but they do not add strength. So if you want to add strength, don't use microballoons. Instead, you will use flocks. Now let's assume you have some fiberglass that's damaged, but it's not only damaged on the facing, but it's all the way through to the core. Can you repair that? Well, yes, you can. You can do it by replacing both the damaged facing and the core. So you're going to have to go a little deeper with your repair. Now, the preferred way to make permanent repairs on any kind of composite is by laminating on new repair plies. So you put on new plies. Now, if you do this over big areas, you might get some warping. So to reduce the amount of warping that you're going to have, what you should do is use short strips of fiberglass, use shorter strips in the bonded repair. So short strips of fiberglass will reduce the warping rather than using large strips of fiberglass. Now, when you're repairing advanced composites, any kind of advanced composites, you do not want to use the same techniques we've been talking about for fiberglass, because it's a whole different can of worms, and they want you to know that on a test. So when you're repairing advanced composites, what you do is use composite techniques. Do not use materials and techniques for fiberglass repairs, because it will result in an unairworthy repair. Now let's talk about honeycomb construction. And when we talk about honeycomb, we're not talking about the song and we're not talking about bees, but we are talking about the shape that we stole from nature. And it's this honeycomb shape that is very, very efficient. And that's why it's used by the bees, and it's very, very efficient. It's light and strong, and that's the shape that we're using. It's this hexagonal shape right here. And anything with this shape is honeycomb construction. It normally consists of a facing panel, a core of honeycomb construction, and another facing panel, and that combination is called honeycomb construction. And this honeycomb core can be metal. In this case, it looks like it's aluminum, or it could be Kevlar or carbon or paper or any number of things, but anything that employs this hexagonal shape with a facing on the top here, the honeycomb core, and facing again, that's called honeycomb construction. And they're used in high-speed aircraft because this type of construction has a very high strength-to-weight ratio and greater stiffness by far than you'd have with a single sheet. Now let's assume that you have trapped water, or suspect that you have trapped water in honeycomb. How can you inspect for it? And the answer is you would inspect for it by X-raying and backlighting testing. Now, you would not use acoustic emission monitoring to look for water. That checks for corrosion and disbonding of the adhesive bond. To check for water, you use X-raying and backlighting testing. Now, honeycomb core is actually formed of ribbons of material. And this is a ribbon of material, and the two ribbons next to each other make this hexagonal shape. So you actually have ribbons of material here with the honeycomb core. And what you do is you look at the ribbons, and the alignment of these ribbons will tell you the ribbon direction. So this is the ribbon direction. It's actually one ribbon of material, in this case metal, and that's the ribbon direction. Now, if you're replacing a section of honeycomb core, as we are right here, what you want to do is make sure that when you put in that plug, the ribbon direction of the original and the plug are lined up with each other. So the ribbon direction of the two must be lined up with each other. Now let's assume you have damaged a honeycomb, but you don't have to replace the core. Maybe it's just a puncture hole, and you're going to put on a doubler. Well, one of the things you need to know is the edges of the doubler should be tapered 100 times the thickness of the metal that you're going to use in the doubler. So you should taper it out 100 times the thickness. Now let's assume you have damage that is less than 1 inch in diameter. You can make a potted compound repair using potting compound when the damage is less than 1 inch in diameter. Now, sometimes balsa wood is used to replace the damaged honeycomb core. If you do use balsa wood, you should make sure that you cut that plug so that the grain is perpendicular to the skin. So the skin goes this direction, the grain goes this direction, and they are perpendicular to each other. Now, another thing you can do when you're making repairs to laminated honeycomb panels is to make use of these little critters right here. These are microballoons, and you use them as
filler material in the resin. Now, microballoons are tiny spheres made up of plastic or glass, and they help you keep a uniform consistency in the resin mixture. Now, a benefit of this uniform mixture is that you minimize the concentration of resin in the edges and corners of the repair, and that concentration could lead to cracking from stress concentrations. So microballoons also, by the way, make the resin mixture less dense, and that reduces the weight and improves the strength to weight ratio. Now, the FAA might ask you if a benefit from using microballoons is that you might get greater concentrations of resins in the edges and corners of the repair, and the answer is no, you get less concentration of resin, and that is a good thing. So what are the good things? Well, microballoons lower stress concentrations, they give you less density, they give you improved strength to weight ratio, but what they do not do is give you greater concentrations of resin in the edges and corners.
Now let's assume that you make a repair to honeycomb. One of the things you always want to do is keep corrosion out of it. So to prevent corrosion inside a repaired honeycomb structure, what you should do is prime that repair with corrosion inhibitor and seal it from the atmosphere. Now let's talk about plastics. And in this particular case, we're talking about very expensive plastics. Well, plastic materials are broken down into two categories. First of all, there's thermoplastic and thermoset materials. Let's talk about thermoplastic materials. These are materials that will soften or flow when they're reheated, but on the other hand, a thermoset material will not soften when it's reheated. It will char or burn before melting. To identify the type of plastic as acrylic or cellulose acetate, what you do is put a little drop of zinc chloride on the plastic. On acrylic plastics, the zinc chloride has no effect, but on acetate, it turns milky. Now, crazing of an aircraft's transparent plastic enclosures, and plastic enclosures, by the way, are windows. It took me a long time to figure that out. Is exhibited, and on the test you need to know this, by a network of fine cracks extending over or under the surface or through the plastic, and that is called crazing. And it's crazy is what the owner finds is when he finds out how much it's going to cost. All right, if no scratches are visible after transparent plastic enclosure materials, we're talking about windows here, folks, have been cleaned, their surfaces should be covered with a thin coat of wax, and that helps protect the plastic. Now, if you want to drill a hole completely through plexiglass, on the test they want you to know that you should use a specially modified twist drill. The drills are different for plastic than for metal. They say it's specially modified. It has a greater pitch here at the point. Now, one problem with plastic materials, what they call plastic enclosure materials, that means windows, is the coefficient of expansion is greater than steel and aluminum. That means they expand and contract more with temperature changes than steel and aluminum does. And that is a problem because they might work inside the aircraft, move around. So if you're installing transparent plastic enclosures which are retained by bolts that extend through the plastic material, and then you're using elastic stop nuts on the end of the bolt, what you should do is that the stop nut should be tightened to a firm fit, then backed off one turn to allow the window to play around inside the mount due to the fact that it has a high coefficient of expansion. It expands and contracts more than the metal does. Now, when rivets are used in the installation of acrylic plastics, adequate spacers or other satisfactory means to prevent excessive tightening of the frame to the plastic should be provided for exactly the same reason. The most common method, by the way, of cementing transparent plastics, that means gluing them together, is the soak method. And what you do is soak them in solvent until they're soft and then put them together. Let's talk about wood structures. One concept you need to know about is, and by the way, isn't this a beautiful wood structure? I think that's a thing of art. One concept you need to know about when we're talking about wood structures is laminated wood. Now, laminated wood is often used in the construction of what they call highly stressed aircraft components, and this wood can be identified by its parallel grain construction. All the grains run together, as opposed to plywood, in which the layers are 90 degrees. So here is a good example of parallel grain construction right here. That's laminated wood, and that's different than plywood when it runs 90 degrees on the grain. Now, information concerning acceptable species substitutions for wood materials used in aircraft repair can be found in, and there's an advisory circular for it, AC 4313-1A, and you need to know this on the test, and that lets you substitute species and tells you what's acceptable as species substitution. Right here behind this is a great example of wood decay. And unlike some other wood defects, decay is not acceptable in any form or amount. In an aircraft, you cannot accept a rotting piece of wood. Now, 3 forms of decay in wood structures are, and they ask you on the test, Dote, Red Heart, and Purple Heart. They do not ask you what these are, they just ask you to name Dote, Red Heart, and Purple Heart, and there are 3 forms of decay in wood structures. Pin knot clusters, little clusters of pin knots, are permitted in wood structure provided they produce a small effect on grain direction. So pin knot clusters are acceptable. Also acceptable are mineral streaks. Now, mineral streaks are okay if careful inspection fails to reveal any decay. Here's something that is not acceptable. Compression failures in wood structures are not acceptable. They're characterized by buckling of the fibers, and they appear as streaks on the surface, and they're right angles to the grain. A faint line running across the grain of a wood spar generally indicates a compression failure. Now, when you're making aircraft wood repairs, special care should be exercised to make sure that you have the proper grain direction, because high shearing strength parallel to the grain should be used to the fullest advantage. So watch the grain direction when you're making repairs. That's what they're trying to tell you by that convoluted question. The strength of a well-designed and properly prepared wood splice is generally provided by the glue. So if you make a wood splice joint, the glue provides the strength. Now let's assume you have a glued assembly and a glue joint fails, it separates and comes apart. Now you'd like to determine, did the glue come apart or did the wood come apart? In other words, did you have glue deterioration? Well, glue deterioration is indicated if the joint has separated and the glue surface shows only the imprint of the wood with no wood fibers clinging to the glue. So if you look at that joint and all you can see is kind of an imprint of the wood, no wood fibers clinging to the glue, that would be a sign of glue deterioration. Now when you are patching a plywood skin, abrupt changes in cross-sectional areas, that's called corners, which develop dangerous stress concentration, should be avoided, and you should do that by using circular or elliptical patches. In other words, avoid corners in your patches. Now let's take a look at an I-beam wooden spar. If you want to save weight and maintain much of the strength, you can route out the spar to reduce weight. So you see how this is routed out, and an I-beam wooden spar is often routed to reduce weight. Laminated wood spars can be substituted for solid rectangular wood spars if the same quality of wood is used in both of them. Now, if you see elongated bolt holes in a spar or cracks in the vicinity of bolt holes, they can be repaired, but the way you have to do it is splice a new section of spar or replace the spar entirely and then drill new holes. Let's talk about hand tools. One type of hand tool we want to talk about is a file. They ask you some questions on the test. How do you use a file? And the answer is you use a file by applying pressure only on the forward stroke, except when you're filing very soft metals such as lead or aluminum. Then you draw the file over the material to remove chips from the teeth. Let's take a look at figure 10 back here in EFA figures, and we'll look at another hand tool, and that is a torque wrench. And they have a particular kind of torque wrench they use on the test that looks like this. You have the handle here, you have a basically a scale type gauge here that tells you how much torque you're putting on it. And this is where the wrench normally ends, right here, and they have an adapter that extends the length of this wrench. And of course that changes the amount of torque the scale should read. So they're going to ask you some questions about that. Now if torque is given in inch-pounds and you want foot-pounds, what you do is divide by 12. For instance, they say a special bolt in a landing gear attachment requires a torque value of 440 inch-pounds. How many foot-pounds would it be? So you take the 440 inch-pounds, divide by 12, and with your electronic calculator you find out by magic it's 36.6 foot-pounds. All right, now let's take a look at another more complicated kind of question we're going to ask you. But first of all, let me set up some information. You're using an adapter on a torque wrench. We showed you that adapter earlier. What you need to do is change the indication on the wrench to find the torque that's actually being applied. And here is the formula you would use to do that. First of all, it's TW equals TA times L divided by L plus A. What in Sam Hill does all that mean? Well, let's take a look at it. TW is the wrench torque. That's what the gauge on the torque wrench should read. TA is the applied torque that you really need to put on the bolt times the length of the wrench before you put the adapter on it. And then you divide by the length of the wrench before you put the adapter on it plus the length of the adapter. In other words, you just have this ratio, the length is on top and the bottom, and you add the adapter to the bottom, and that gives you the ratio, or gives you actually the wrench torque, the gauge torque. Now let's take a look at a way they're going to ask you a question about this. First of all, they're going to send you to figure 10, and we've already been on figure 10. And they tell you a trunnion nut requires a torque of 320 inch-pounds, and that's going to go up here. That's what you really want to apply, is 320 inch-pounds. And they say you're using a 2-inch adapter, and a 2-inch adapter on an 18-inch torque wrench. So you have an 18-inch torque wrench. So the length of the torque wrench is 18 inches. You actually want to apply 320 pounds or inch-pounds of torque. And the question is, how many foot-pounds of torque will you apply? Well, let's figure out how many inch-pounds first, and then we'll figure it out. Okay, again, we have the applied torque that we're really trying to get is 320 inch-pounds. The wrench is 18 inches long, fits in both places. Add the 2 inches for the adapter, and then work all of this out with your electronic calculator. 320 times 18 comes out to 5760, and 18 plus 2, I can use my calculator and figure out that comes out to 20. And then you use your electronic calculator, take the 5760 divided by 20, and you get 288 inch-pounds. But you want foot-pounds, so take the 288 inch-pounds divided by 12, and that comes out to 24 foot-pounds. Now, believe it or not, you and I have covered everything you need to know about structural repairs on the FAA written exam, so now you're qualified to repair something exotic, like a Ford Trimotor.